Okay, problem 10.4. Suppose Q is a n by n symmetric matrix, and the first part is to show that there exists a Q conjugate set of D1 through Dn, such that each one of them is eigenvector of Q. The second part asks to show that suppose Q is positive definite, and show that if the D1 through D0 is Q conjugate set, then and also they are not just the Q conjugate, but they're also orthogonal to each other, then each of these di's is eigenvector of Q. Okay, so for the part A, we check that suppose we know so for the first part, since Q is symmetric, we know that the Q has eigenvalue decomposition, meaning that we can find n orthogonal eigenvectors, and that's just vectors, and and every one of them has a corresponding eigenvalue, which is real. But all these eigenvalues could be the same. Some of them could be the same. But anyway, we have this. So the Q equals this. Okay, so this lambda is a diagonal real-valued diagonal matrix, and this Q is a orthogonal matrix. So we just extract the columns of this Q. We call the columns of this U to be D1 through Dn. Then this D1 through Dn are eigenvectors. Okay, so this is the only thing we need. So the Di for each of these vectors, it has a corresponding lambda, which is the ith diagonal entry of that matrix that just drawn. And we will have this property, right? Because Di is the eigenvector. Well, because the because we know this such a set exists, we just need to show that they're also Q conjugate. Well, to show that they're Q conjugate, we just need to show that there's the Q inner product of d and dj is equal to 0 for any I not equal to j. But this is equal to that because the Q dj is just the lambda j dj, since the dj is eigenvector, right? And then we have a di dj, but so lambda times di dj. But since the di dj's are orthogonal to each other, they came from the same orthogonal matrix U, just two different columns. So they're orthogonal to each other. So that's why this essentially is equal to 0. And this proves that the di dj are Q orthogonal. And since this is true for any I not equal to j, we can prove that these di's are Q conjugate. So that's the part A. The part B shows that if D1 through Dn are orthogonal, well, if they are orthogonal, then we can normalize them and make them a standard basis for Rn. Or if you don't want to normalize them, it's fine. We're going to normalize them later. The point is that for every I, the Q di, which is forget about what it is, but just think it is a vector in Rn, and then it should be written. It can be written as a linear combination of the bases, because this is like orthogonal, so we can form them as the basis. Well, the way to form them as basis is that, if they are like standard normalized basis, then we just need to multiply the inner product of this, take the inner product of the Q di with every one of the bases, and then this will be the coefficient for the basis. But since these di's are not necessarily normalized, so we just divide this to normalize them, because this square here one can go to this, one can go to this, then they will make those di's normalized. But this is how we can express every vector using the di's, and specifically we can express this Q di using this form. All right, so now suppose these di's are Q conjugate and they are orthogonal. So let's see what happens. Because they are Q conjugate, so that means if I multiply this with dj for some j different from I will get 0. So that means I will multiply this, I will get 0. But on the other hand, we can see that the if I multiply dj on this side, I get 0. Then that means I multiply dj on this side, I will also get 0. So I multiply dj on this side, I will also get 0. Well, because when I multiply dj to the right-hand side, I only have one term left, since these are merely just some scalar constant or coefficient. And this is what the vector is. But when you multiply di some dj to this, there's only one term lives, right? All the other n minus 1 terms will be gone, since these di's are orthogonal to each other. So the only one that is left is that di term. Okay, so so in this case, we can see that the so I should say in this way. Since we can rewrite it in this way, so we know that the di and dj, since they are q orthogonal, so for look at this will be 0 unless I is equal to j. So that means the whole sum here will have only one term left, which is the ith term, and that ith term is essentially just that. Okay, so now so I should just forget what I said earlier. Here, up to this step, it's okay. And then when we look at the sum, the term in the sum, we realize that only one term lives because the di dj's are q conjugate to each other. So this will be 0 unless I is equal to j. And that means there's only one term lives in the right hand side, and that term is this term right here. And now look at this term, we'll see that this is nothing but just a scalar, okay? And the q di equals to some scalar times di, that means di is the eigenvector. Okay,